Okay, Rahul, Suprabhatam. Okay, so fine. So we have actually maybe discussed about maybe the Bayesian classifier. Okay, maybe for continuous as well as for discrete maybe features. So that was our first module. Okay, mainly, and now we will go to the second module. So the second module, we will see what is actually the maybe the issues or maybe the challenges with a Bayesian classifier that we have actually seen. Okay, so we for a Bayesian classifier, we assume that okay, we know the prior probabilities and we know the class conditional densities or probabilities. Okay, because these are the two values. Okay, that we actually require in order to find the posterior probability, and based on which we are actually maybe designing the maybe or finding out the decision surfaces, okay, or decision regions, etc. Okay, so we can actually maybe design an optimal classifier if we know these two classifiers. So that is a very important thing. So then we know that so what information, okay, we are actually having. Okay, and how we can actually calculate these probabilities are actually one thing that we have to maybe look into. Okay, but the thing is that rarely we will have actually a complete information about the prior probabilities and maybe the class conditional densities. So the prior probability, maybe we may be having some maybe prior information if you are having with respect to the problem that we are actually trying to solve. But again, it is difficult maybe in the case of maybe class conditional densities where we will not have that maybe detailed information or maybe the minimum required information maybe to come with a very good classifier. So that is actually the challenge before us. Then now we will see how we can actually calculate or maybe how we can find out methods that will give us an idea about maybe these values so that we can apply the Bayesian maybe classifier. So one thing usually in a supervised learning method, okay, that is given to us is actually the training data. Okay, so we assume that we are actually provided with okay, a set of sample data. Okay, we call generally it is a training data. Okay, and so that will only be available. Okay, so that is actually one the only data or information that we can actually use to maybe find out these probabilities. Okay, so one approach that we can actually follow if we are actually are available with the training data is we can use these samples, okay, in the training data to estimate maybe the unknown probabilities, okay, and this probability densities. Okay, so that is actually one way of maybe approaching this particular problem. Okay, and then suppose we are actually trying to estimate these probabilities and probability density values, and once we maybe find out, okay, using the training data, we assume that okay, the resulting estimates as if they were actually the true values. Okay, because this data, okay, may be generated by a particular probability density or the prior probability may not be the exact one. Okay, but we are assuming that whatever we find out from the given training data, we assume that they are actually the true, okay, densities or true probabilities in the realistic situation also. So that's an assumption only. Okay, so the, and we actually go ahead with that particular maybe say assumption that this is going to be the best one that is actually available to us. Okay, but there can be many issues. Okay, because that depends on maybe the training data. So that means whether the available samples okay seems too small, so that can be an issue. Okay, because we have actually we can have two categories or maybe multiple categories of problems. So there can be a situation whether we have enough maybe samples from each of the category. Okay, maybe in order to design the say the pattern classification system. So that is one issue. Okay, availability of samples is actually one issue. Okay, and another one is actually maybe the dimensionality of the feature vector x. Okay, so when we are having a large, okay, dimension, okay, for the feature vector x, that can also have an issue. Okay, so maybe our method may not be actually so the whatever we actually calculate for the probabilities, okay, may not be the exact fit, okay, or they may not be representing the reality. So that is a drawback actually, maybe or maybe the challenges that is actually before this particular say maybe attempt. Okay, so the problem can be simplified. Okay, so we assume that we will be maybe we can simplify this particular problem, okay, with respect to maybe these challenges. So that is okay. So one assumption that we can actually maybe make is, maybe for a simplification, is that okay, suppose we can reasonably okay assume that okay, probability of x given wa, because that is a class condition probability, which is a very crucial one. Okay, and we assume that suppose we assume that okay, we can actually approximate okay that particular class conditional density into a normal density. Okay, suppose, okay, and we know that the normal density, okay, if the distribution of maybe this class conditional density is actually a normal density, then we can say that we can actually represent that with a mean value and a covariance matrix, so that we have actually seen, because that is the way they are the two parameters actually used to represent a normal density. So if we assume that the class conditional density can be is okay close or maybe representing the normal density, okay, then we can maybe simplify the problem. Okay, so actually what we have to estimate is, we have to estimate or we have to find out this class conditional density function, but that is going to be a challenging one. So what we will do is, we will try to simplify the problem. Okay, and we assume that okay, instead of finding out an unknown function, okay, because we don't know what is our original function that actually maybe say generated, okay, or from which we actually obtained the training data sample. Okay, but what we will assume that we assume that this particular function is closer to maybe a normal density function. So we know that a normal density, we know the complete analysis. Okay, so we assume that there are two parameters, okay, the mean vector and the covariance matrix. So we try to find out estimating these two, okay, from the given data. Okay, and then we will go ahead, okay, or we'll go ahead with the classification, okay, or applying the Bayesian maybe through that particular say path. So that is actually the way we will be going ahead. So this is one thing. Okay, and okay, so if that is the assumption that we make, okay, suppose we are having a collection of samples, okay, we are given, okay, so that means when we assume data, you can just maybe bring into mind, okay, about the tabular data set that we have already seen. We'll have a set of rows, and we'll have a maybe one of the columns as a class information, and assume that there can be w1, w2, w3, okay, c number of classes, and assume that we can have a maybe grouping of okay all the w1 classes, w2 classes, w3 classes, okay, maybe for analysis purposes. So you have to bring in that particular maybe say data set into your mind. So then assume that we are having a C data set, so that means corresponding to maybe W1, okay, W2, etc. up to WC. So there are C categories. So that means we assume that the whole data set is actually, we are having divided into D set data sets of the D1, D2, etc. up to DC. Okay. So that means D1 corresponds to all the tuples or all the feature vectors corresponding to the first class W1, and D2 corresponds to W2, and so on. Okay, and so now we make again an assumption that okay, suppose you consider any maybe there's such a data set, okay, a DJ, okay, and we assume that they are actually drawn independently, okay, according to this particular probability distribution, because this is a probability distribution that we are actually trying to find out, or we are trying to approximate it. So we are trying to approximate, we are making an assumption that D1 is actually independently, okay, sampled, okay, with respect to D2 and others. Similarly, D2 is independently sampled with respect to the other data sets. Okay, so that means there is a principle called okay, IID principle. Okay, so that is independent and identically distributed random variables. We assume that. Okay, so we assume that the samples are independent because they are independent and identically distributed means we are assuming that all of them are actually taken from the same distribution probability of x given wa. And if we assume that as a normal density, then we assume that all of them actually follow a normal density function. So that is a independent and identically distributed maybe random variables or IID. Okay, concept. So that is again another assumption we make. Okay. So with that particular IID, okay, assumption, assume that we have a, okay, assume that we are having P of maybe X given, okay, Wj as having a parametric form. So that means we assume that suppose that's going to be any form, whether it's a normal density or maybe any other density. But as we are assuming that we are having as a parametric form. Okay, then we represent that parameter. Okay, assume that there can be set of parameters. So assume that each of the parameter vector we represent using a letter theta j. Okay, so theta is the maybe the variable. Okay, so we are representing a set of the parameters. Okay, so theta j means that corresponds to the wj. Okay, similarly, you can have theta 1, theta 2, etc. up to theta c. Okay, so that is for each of the maybe classes. Okay, for each of the classes, we'll have a say parameters. So that means we are assuming that okay, probability of x given wj is approximated to a probability density. Okay, so it's a normal density of mu j and okay sigma j. Okay, where we have a corresponding parameter, okay, vector for this normal distribution. Okay, it consists of, we know that for a normal distribution it consists of mu j and sigma j. Okay, because they are the two parameters that completely define the a Gaussian distribution or a normal distribution. Okay, so that is a concept of parameter vector theta j. That's an additional maybe term that we will be using. Okay, so that is representing the probability distribution. Okay, so that means if we are maybe considering that aspect, then the probability of x given wj, we can maybe show the dependence of, okay, on theta j. So that means we know that this particular probability is now dependent on the theta j. So that is actually this particular notation, probability of x given wj comma theta j. So it actually shows a dependence on the theta j. Okay, so that is another notation. Okay, so then what is our job is actually, okay, we use a training samples, that is a given samples to obtain good estimates, okay, for the unknown parameter vectors. Okay, so we can consider each of these samples corresponding to each of the classes w1, w2, w3, etc. to wc, and for each of the classes you can actually find out the corresponding parameters theta 1, theta 2, etc. up to theta c. So that is actually our job we have to consider. Okay, so that is the problem before us, that is finding out the parameters. Okay, so that is what we will be discussing maybe in the first part of this second module. Okay, and now, so that means we assume that the parameters for the different classes are actually functionally independent. Okay, so because we already made an assumption that d1, d2, d3, etc., dc are actually independent. So hence their corresponding probability distributions are also maybe independent. Okay, so that is actually, you can say that then the parameters are also independent. So that is actually another assumption that we are actually keeping. Okay, so that is generally about maybe so a very brief introduction on why we are actually going to this particular aspect. Okay, I think we'll just share. Okay, so so that means we have actually two different types of techniques. Okay, maybe in finding out the parameter, maybe parameter that we have discussed, maybe the theta. So there are two methods. So one method is actually called the maximum likelihood method. Okay, so there's a maximum likelihood method, and the second method is actually called the Bayesian parameter estimation. So maximum likelihood and Bayesian parameter estimation is actually maybe the first part of our second module. Okay, so that is actually what we are going to discuss. So that means we'll quickly go through. So we are assuming that maybe we'll see some of the already discussed concept, but we'll quickly go through. So we are assuming that data availability, okay, is a very crucial thing. Okay, so we could design optimal classifier if we know, okay, the prior probability and the class conditional densities. Okay, but we rarely have this complete information. Okay, so that is the case. So that means design a classifier from a training sample. Okay, so okay, maybe the problems that we have actually discussed. Okay, samples are too often small. Okay, and other issues. Okay, and so now, so if you are having a information about the problem, okay, suppose we are having some prior information about the problem, then we can actually find out maybe the prior probabilities. If there's something about the distribution, then we have to find the parameters to characterize the distribution. So the same thing that we have discussed. And so now the normal density assumption, so that is actually the normal density equation, and we know that they are characterized by two parameters. And there are two estimation techniques. Okay, one is called a maximum likelihood okay estimation and a Bayesian estimation. So, okay, and interesting thing is that you can actually apply any technique, any of these, maybe depending upon the availability, okay, of data, or maybe other things, but the results are almost identical. Okay, but the approaches are actually different. Okay, so that is maybe another interesting thing. So the results are going to be very identical, and maybe the approaches, how they actually calculate each of this method, calculate the theta values, that is theta j values for a wj class, is actually different. So that is we will see, okay, how they are actually differing. uh, so one major maybe so this will be clear when we discuss the methods in detail, but from a very overall point of view, we can say that the parameters in ml estimation, okay, are fixed. That is, ml means a maximum likelihood. Okay, sometimes in some textbooks you see mle. Okay, so mle represents a maximum likelihood estimation. So parameters in mle are actually fixed but unknown. Okay, anyway, they are unknown because we have to find out the unknown. That is actually our aim. But we assume that that they are actually fixed. Okay, so that is one assumption. Okay, and we have to find out the that particular fixed value, which is actually the optimum one or the best one. So that means the best parameters are actually obtained by, okay, maximizing the probability of obtaining the samples observed. So that we will see. Okay, anyway, we assume that the parameter is actually fixed, and now we have to find out the best parameter in such a way that okay, so that parameter that we select, okay, that we select for our final maybe designing of the classifier, we assume that that parameter will be maximizing the probability of obtaining the samples observed, because we are actually we are actually given only the training data set. That is a main source of information we are having. Okay, so we have to find out a parameter that maximizes the probability of obtaining the samples observed. Samples observed is actually the training data. So that is actually the main maybe the very critical maybe point in maximum likelihood estimation. Okay, but when you consider Bayesian method, okay, the parameters are actually considered as random variables, and they are having some non-distribution. Okay, so that means in Bayesian estimation, we are actually essentially we are calculating a probability distribution. Okay, but in MLE method, we are actually finding out the optimum value or the best value. That is a difference. In one way, in Bayesian method, we are trying to find out a random variable and its distribution. But we know that whenever you consider a distribution, that distribution will have a maximum value, and that maximum value and the maximum value that or the best value or the parameter value that we select in the MLE method, both are going to be identical. So that is why we already told that. So that means both the methods actually return the identical results. Okay, but they are actually finding out in different ways. Okay, and so that we will see maybe in detail. So in either approach, so that means whether you are using MLE or Bayesian estimation, finally we know that we will be using this probability, that is posterior probability. That means probability of Wi given x, okay, for our classification rule. Okay, whether you are finding out a Bayesian say distribution and maybe using that for finding out the posterior probability, or you find out a best parameter for MLE using MLE and using that for finding out the maybe the posterior probability. Finally, the classification is going to be based on whether this is greater than probability of, okay, Wj given x, okay, where I is actually not taken to say. So that the rule that we have already actually seen. Okay, so that is actually essentially what we are actually trying to solve. Okay, okay, and so now we will go to the maximum likelihood estimation. Okay, so there are some advantages for MLE. Okay, so when it is a good convergence properties as the sample size increases. Okay, so that is one advantage of maybe this particular method, and it is actually very simple. Okay, than okay other alternative techniques. So these are some of the advantages of maybe MLE. Okay, and now we will see how that maybe in general how we can actually find out the best theta value. Okay, that actually gives the best result. Okay, so we are assuming that we have C classes. Okay, and we are assuming that they are actually approximated to normal densities. Okay, and so this notation also we have seen, that is the class conditional densities are actually and dependent on the theta values also. So that is also we have seen. And now when you look into theta value, okay, we have seen that that is going to be a vector. Okay, again, okay, with the okay the parameter vector. So that means you have a mu j and a sigma j. Okay, so that is the case. And similarly you can have that mu j for, okay, 1 2 3 etc different cases. Okay, so that is actually just an expansion of that one. Okay, anyway, that is not important for us. Now what we will use, you will be using this particular information provided by the training samples to estimate maybe the same thing that we have discussed. We have to find out theta 1 theta 2 theta etc up to theta c for each okay maybe categories. Okay, so that we have already discussed. So that is actually the maybe the case. And now so we have actually seen that okay we have made an assumption that we have a d is equal to, okay, we have a d1, okay, d2 etc up to say dc. Okay, and we have made an independent assumption also, IID, okay, assumption also. So if considering that particular thing, okay, suppose we have a D contains samples x1, x2, etc. up to xn. So that means you are taking one of these, okay, one of these, okay, one of these as maybe capital D, okay, and we assume that there are n samples. Okay, so that means there are n training data samples are actually present in a single D. Okay, so if that is the case, then how we can actually define, okay, so what is the probability that okay you are actually we are assuming that your theta is actually maybe given. Okay, and then we are actually looking at the probability, the likelihood that that theta generated this samples, okay, in D. So that is this particular probability represents. So we are actually trying to see that okay, what is the likelihood for a theta. That means a theta means a theta consisting of mu I and a sigma values. So what is the likelihood that that theta generated this particular data set? So that may be for a particular category. So that is actually this particular probability. Okay, maybe represents. So that means we have made that each of these x1, x2, etc., etc. to xn are actually independently, okay, drawn. Okay, So that means that can be maybe written as a product, okay, because they are independent. So that means that is we have a k is equal to 1 to n probability of xk given theta. So xk is x1, x2, etc. up to xn. So because they are actually okay, the independent. So that means probability of d given theta is called the likelihood of theta, okay, with respect to the set of samples. Okay, so that is actually one probability that we define. Okay, so and now what we have to maybe what MLE maximum likelihood estimation is actually doing is we have to find out the theta, okay, which actually maximizes this probability. So that means so ML estimate of theta is actually by definition of the value that maximizes probability of D given theta. So that is actually the maybe what we are actually looking for. So usually we represent such a theta by theta cap, okay, by the notation theta cap. So where theta cap is actually the maybe the theta vector, okay, that actually returns or that will maximizes probability of the given theta. So that is maybe the concept of maybe max the best value. So the best value that we are looking is actually theta cap. Okay, so that means it is a value of theta that best agrees with the actually observed training samples. Okay, so we are assuming that because we don't know the exact distribution. So with the available data, okay, so it means in the form of a training data set, we are trying to find out which parameters. That means maybe, for example, in the case of a normal density, which mean value and which covariance metrics might have generated the given data in the best fashion. Okay, so that is why we are trying to maximize the probability. Okay, and maybe we are making this particular assumption for particular parameter. Okay, so that is actually essentially what is actually done in maybe maximum likelihood estimation, finding out the theta cap. Okay, okay, so this is maybe an example, okay, maybe from our textbook. Suppose we are having, okay, a set of one-dimensional data. Okay, suppose we have a one-dimensional training data. Okay, so that means these are actually the one-dimensional training data. Okay, so they are the one-dimensional training data. Okay, and ultimately what we are trying to look is actually we are trying to look for the probability density, okay, function which actually generated, okay, or from where we might have independently, okay, drawn these samples maybe in the other way. Okay, so each of these maybe dotted, okay, lines actually represents different possible probability densities, okay, that might have generated maybe these samples. Okay, so that is a case. Okay, so that is maybe the first topmost curve represents it. So so we are assuming that they are drawn from a Gaussian, okay, particular variance, but unknown mean. Suppose they are having there can be different cases because we are having two parameters, mu mean value and the variance. So there can be cases of maybe some mean value different and same variance, or we can have arbitrary values, any value for sigma or any value for mu. Okay, all such possibilities are actually there, but this is just an example to give an idea that for a particular variance and but unknown mean value. Okay, so these are four because so these are just four cases, but we can have infinite number of such probability distributions that we can consider maybe here. Okay, there are many possibilities we can actually consider. Okay, just for an for maybe to make it simple, they have actually included just four cases. Okay, so that is the case. And now if you look into this particular diagram, so this actually represents maybe the probability that we are actually trying to maximize. Okay, so that means so that is along this one is actually the theta. Here you have it's a the single the feature, okay, that we have considered, but this is a theta. Okay, so the theta, and for which theta we are getting the maximum probability, that is actually the theta gap. So that is again what we have actually discussed. Okay, so that is the case. And this is actually maybe usually for a calculation, for analysis, okay, purpose, it is always better to take a log of this function, okay, log of this particular probability, and we call this as likelihood value, okay. So it is called a log likelihood, okay. So it's a common terminology that you can say, log likelihood. So that means it is represented as L of theta. Okay, so that is so we find out a log likelihood, okay, L of theta. Okay, so because that is that we will see why what is advantage of maybe taking the logarithm, that we will see later. Okay, but anyway, even if you plot the log likelihood, okay, we will get a figure like this one, and there also you can see that the same, okay, theta will generate the theta cap. Okay, so that is a point. Okay, so that is maybe the concept of maybe this particular maybe the importance of maybe these diagrams. So I think that is clear from all these diagrams. Maybe the concept of theta cap, the concept of log likelihood, okay, maybe maximizing which parameter we are trying to find out, etc. Okay, so that is a case. Okay, and I think we will stop today here, and we will see what is actually how this parameter theta can be calculated. Okay, maybe in the next class. Okay, so thank you for listening.